This sword was forged sometime around 1700. It is harder than modern steel, sharper than a surgical blade, and more flexible than anything Europe could make at the time. In 2006, scientists dissolved a piece of it in acid and found something inside that shouldn't have been possible: carbon nanotubes, the same material NASA uses today. The blacksmith who made this died 300 years ago. He had no microscope, no laboratory, no periodic table. He just knew it worked, and then the knowledge disappeared. Carbon nanotubes are one of the strongest materials ever discovered. They're lighter than aluminum, stronger than steel, and NASA has spent billions trying to manufacture them reliably. The year they were officially discovered, 1991. The year they were first used in a weapon, somewhere around 900 AD, by a blacksmith in Damascus who had no idea what he was making. This is the story of how a technology was accidentally invented, accidentally perfected, and then accidentally lost, all because of a mine in southern India that ran out of ore. Let's be precise about what Damascus steel actually is, because most videos get this wrong. Damascus steel is not a technique, it's a result. The technique is called Woots, and it wasn't invented in Damascus. It was invented in India, possibly as early as 300 BC, in a region that is today Tamil Nadu and Telangana. Archaeologists have found steel-making furnaces in Sri Lanka, carbon-dated to 300 BC. These weren't primitive hearths. They were wind-powered blast furnaces, positioned to face the monsoon winds, using natural airflow to reach temperatures that Europe wouldn't achieve for another 1,000 years. The steel they produced, Woots, had a carbon content of around 1.5%, high enough to make the metal hard, but by all logic of metallurgy, also brittle enough to shatter on impact. It shouldn't have worked as a sword blade. And yet, when Crusader knights first encountered Damascus blades in the 11th century, they reported something they couldn't explain. The swords of their opponents could cut through European armor while bending, not breaking, on impact. One account describes a blade slicing a silk scarf in half as it floated to the ground. Not a party trick, a demonstration of edge geometry that modern metallurgists still struggle to replicate. In 2006, materials scientist Peter Paufler at the Technical University of Dresden dissolved a fragment of a 17th century Damascus sabre in acid. What was left under the electron microscope stopped his team cold: carbon nanotubes encasing iron carbide nanowires in a pattern that explained everything: the hardness, the flexibility, the edge retention. The blacksmiths hadn't been making steel. They had been accidentally manufacturing a nanomaterial composite. But here's the part no one talks about enough. They had no idea. The nanotubes weren't the goal. They were a byproduct of a very specific combination of factors that the smiths had learned through centuries of trial and error, without ever understanding the chemistry behind it. And that's exactly why the knowledge was lost. The Woots cakes shipped from India to Damascus contained trace amounts of specific metals: vanadium, chromium, manganese, cobalt, nickel, not added deliberately, present naturally in ore deposits from specific mines in southern India. During the forging process, alternating hot and cold cycles that the smiths had perfected over generations, these impurities acted as catalysts. They triggered nanotube formation from the organic material used in the furnace: leaves, wood, plant fiber. Sometime around 1750, those specific ore deposits ran out. New sources of iron came from different regions, different mineral profiles. No trace vanadium. The smiths used the same techniques, the same temperatures, the same cycles. The nanotubes didn't form. The blades came out, just ordinary steel. And no one understood why. Modern metallurgists have been trying to reverse engineer Damascus steel since the 19th century. And here's the uncomfortable truth: we still can't fully replicate it. Not because we don't understand the chemistry. Paufler's 2006 study, published in Nature, gave us the structural blueprint. The problem is the ore. The specific combination of trace metals that triggered nanotube formation came from mines that no longer produce steel-grade ore. Some researchers have achieved partial replication, producing blades with visible carbide banding, similar surface patterns, comparable hardness. But the nanoscale structure, the accidental nanotechnology? Not yet. There's something almost poetic about this. For 800 years, smiths in Damascus produced the most advanced material on Earth, without knowing what made it work. The moment they tried to scale up, change suppliers, cut costs, the magic vanished. And the knowledge they had, the temperatures, the cycles, the timing, was the wrong knowledge. It described the process, not the mechanism. When the ore changed, the process stopped working, and they had no framework to understand why. There's something almost poetic about this. For 800 years, smiths in Damascus produced the most advanced material on Earth, without knowing what made it work. The moment they tried to scale up, change suppliers, cut costs, the magic vanished. And the knowledge they had, the temperatures, the cycles, the timing, was the wrong knowledge. It described the process, not the mechanism. When the ore changed, the process stopped working, and they had no framework to understand why.